Hello, this is Fahim, and I'm going to present my paper. The title of my paper is Privacy Preserving Learning via Data and Knowledge Distillation. Here's the name of the authors and the co-authors. And it's my pleasure to present in the conference DSAA 2023 special session, PSTDA. So this is the content and overview of my presentation. So the introduction, nowadays due to the recent evolution of deep learning and machine learning, and the generative models like ChatGPT, people are getting more interested in using machine learning models in medical diagnostic or image analysis or analysis task. But the problem with this medical diagnostic task using machine learning is that data contains sensitive patient-related information, and hospital use direct or indirect identifiers to tag or identify those data. And widespread use of those sensitive images and high memorization capacity of the pre-trained complex machine learning models present significant privacy risk. So nowadays, like most of the medical organization are really careful about like data storing and privacy during data storage, but they tend to ignore the problem of models privacy. So how it can leak information? Knowing a patient's record used to train a model associated with a disease reveal patient's ailment. It lead to advanced attack in the future like attribute inference, feature extraction, and data poisoning. So if we know that patient X's data was used to train a cancer prediction model, then the adversary may also know that the patient might have cancer. So the problem is memorization. Models like tend to memorize each and every data point due to the larger capacity, and they tend to overfit. And One solution is to use appropriate model capacity that also can maintain similar utility. And people might assume that trusted APIs like Google, Amazon machine learning APIs are immune to MIA attack, but Reza Shokriatel and some of his collaborators and some of the predecessor papers also showed that and descendant papers also proved that black box models are also immune to MIA attack. So there are two type of membership inference attack: white box and black box attack. And the membership privacy is a privacy that protects model against membership inference attack. So in case of MIA, adversary gain information about an individual by knowing that their data was used to train a predictive model. So white box attack exploits the gradient difference between train set member and non-members, because when the data is from train set, the gradient will be different, and when the data is from train set, the label prediction confidence value will be different than the data that is not from train set. So our goal is like we will utilize the in a synergy of collective distillation, data and model distillation to sanitize private knowledge so that the resultant model is private, efficient, and well generalized. So the contribution is that we are able to ensure target model compactness and membership privacy at the same time. So previous approaches don't focus on like model compactness, but we focus on model compactness so that this model can be directly deployed in the device, and it can ensure like inference efficiency. And is feasible or practical because it does not require any public data and restricts repeated access to private data, which some of the previous work failed to do. And distilled data facilitates class balance, because whenever we generate distilled data, we ensure that there is equal number of data point per class, which promotes fair training. And we try to use lightweight model so that the appropriate model capacity and soft label during distillation helps to promote generalizability. And the utility improvement of 834 and 6% in the CIFAR 10, 100 and MNIST with 50% privacy, 50 to 53% privacy leakage shows that the privacy like it is able to ensure better accuracy privacy trade-off, where like 50% privacy leakage is close to random guess of a dummy classifier. So resultant student model is efficient as it requires half the model and data sets to train, and is also robust to membership inference attack. So the related work are can be divided into three subgroups like empirical defense, theoretical defense, and knowledge transfer based defense. So the empirical defense are like they're based on instructive theories. And fundamental principles. They are empirically optimal, but they are optimized based on utility. So if we want to ensure privacy, then it has a huge toll on utility. So white box regularization and adversarial regularization are examples of empirical defense. And theoretical defense are like they are based on probability theory, and they can provide a theoretical guarantee for privacy, but they are not optimized based on utility. And they like DPSGD and PATE add noise to the gradient of the model, which deteriorates the utility of the model. And noise transfer based defense like KCD and Selena They require repetitive access to the training data, which might be risky, and it might not work well if there is a duplication in trained data or class imbalance. And DMP requires additional public or reference data, and also requires data tuning based on like entropy to perform better. And synthetic database DMP does not perform well. So data condensation, it is not directly related to membership privacy, but Long et al.'s paper demonstrated how it can be, how data condensation can like theoretically related to differential privacy. But their deliverable was data, not moral, and they assume that adversary has access to the distilled data, which might become vulnerable in worst case. So we combine models, knowledge transfer with privacy-oriented data distillation, restricting adversary access to distilled data. So intuition is that we want to produce similar prediction, confidence score and gradient value for member and non-members of the train set. And we will use distilled data instead of private data to transfer the knowledge to student. And we want our student model to be lightweight and efficient so that it can reduce overfitting. The three type of networks are used during the process. We can see the large heavy teacher model, red, the green student model, and some of the expert models are also used. Expert and student have the same architecture. So expert and student are used during data distillation, and teacher and student are used for knowledge distillation. So train large capacity teacher model on the private data, and distill the private data to get a small distilled data, which ensure then we transfer the student heavy teachers model to the student based on the label distilled data, where the teacher will be used to generate the soft labels. So the main intuition between the distilled data generation, according to the picture, we try to reduce the large data set D to a small data set S, so that it can retain same performance on the distilled data. Now, whenever the experts are trained on the real data, so we use a set of models as experts. So we use the expert to generate model parameters during training and store the parameters as buffer. Those safe snapshots will be the ideal trajectory that our model will follow, which will guide the optimization of distilled data, where student will be used to test the performance. So we use a parameter loss following parameter matching loss following some data distillation work, but the student will follow the same path of the expert, and in the process following this path, it will generate a distilled data. So in the image, if you look at the image carefully, the red rectangle and the parameters in the rectangle theta star t indicates the parameter of the expert network whenever they are trained on real private data. So we train 80 to 100 expert networks on the real private data and store only the best parameter for each time step t as theta star t. And the theta ft indicates the student model f's parameter while training on distilled synthetic data. We try to minimize the distance between expert models parameter trained on private data and student models parameter trained on distilled data. So in the whole process, the input will be private real data and the output will be distilled synthetic data. So we train expert on safe theta star t, a snapshot of ideal behavior that the student should follow while optimizing distilled data S. We fetch a random parameter theta star t and initialize student f with the theta star t value, and then train theta f for n iteration, where S is optimized using the parameter matching loss. This loss is an L2 loss, which calculates relative error between learned student model theta ft plus n after n and a distillation epoch, and known feature parameter theta star t plus m after designated m epochs. So this L2 loss will measure the similarity and divide by the distance of the expert covered to normalize the distance. So we initialize synthetic data S with real image X, and we update pixel of S using differentiable augmentation, which so that it can be back propagated to minimize the L2 loss. And if we look at the equation in step 7, theta f t plus n plus 1 of student indicates the updated student parameter after n step of gradient descent, and during each gradient descent step we choose different mini batch of the private data to come up with the to optimize the distilled data, so that we can preserve the diversity of the private data. And the second step is the knowledge transfer task, where we transfer private teacher knowledge to a smaller student using distilled data. So we use the private teacher to generate soft label of the distilled data. Then we transfer the private teachers private knowledge and sanitize it and transfer it to student model using the label distilled synthetic data. So we keep private data untouched during final student training, as model tend to generate like high confidence scores for scene data prediction. So we use distilled data instead of real data, assuming that adversary cannot access it, because we don't our output or deliverable is not data, but our deliverable is model, and the distilled data is stored in a temporary basis during the whole process. So we train large protected teacher model T on whole private data D. Then we use the trained teacher model T to compute soft level of the distilled data S. um, like we use high temperature tau to smooth out the logis distribution. But why do we use high temperature? Because the main reason for membership privacy leakage is that the model's logit value will be extremely confident in presence of scene data. So high temperature can smooth out the distribution. It works as a strong regularizer, which can help to sanitize the knowledge, and it helps to maintain a balance in the confidence value of the prediction among class tables. Then we train reinitialize student model F, like based on the soft level and prediction. So we train student model based on soft like data point S of synthetic distilled data S and soft level TS. So we use two loss. The main loss is the LF in the step 3. There are two parts of the loss. One is lambda KL. In lambda KL, we use Kalbeck-Leibler divergence or KL divergence to measure the similarity between the prediction and the soft level distribution. And in the cross entropy loss, we try to match the prediction and the ground truth level or the true level Y. So we use an alpha hyperparameter, which is used to control the trade-off between the privacy and utility. It is also used to control the dependency on the soft level TS and the ground truth or hard level Y. So whenever we increase dependency on the soft level, the model reduces privacy leakage. But whenever we increase dependence on the true level, the model tend to leak more private knowledge. So we try to come up with the optimum alpha hyperparameter value so that it can ensure better privacy utility trade-off. So in the experiment, different data set was used. So the most common data set were CIFAR 10, 100, and MNIST, which are commonly used in computer vision and privacy analysis task. And in case of distilled data, we generate 10 image per class for CIFAR 10, and MNIST it is 500 image, and for CIFAR 100 it is 5,000 image. So instead of 50,000 or 60,000 image, we can use only 500 image to come up with similar performance. And in case of model, like previous work used LXNet, ResNet, or DenseNet. So we used a lightweight component with 3-layer, which has like 320,000 parameter instead of like 2.4 million parameter in the previous approaches. So as the expert, we use 80 to 100 coordinates to store the buffer where the student coordinate will follow. And they have the same architecture. So as the teacher, we use ResNet 50 for CIFAR 10 and 100, and ResNet 18 for MNIST. So in case of membership inference attack, to design the adversarial or attack model, we replicated Nasser et al.'s black box and white box attack models, like attack paper. So in the white box model, the model has access to the each and every layer's output, the gradient information, the prediction confidence, all. And the black box model, the adversary has only access to the label and prediction confidence. For example, for the MNIST, we split it into 25,000 and 35,000 data, where 25,000 data is reserved for attack model training and 35,000 is used for regular training model. In the qualitative analysis, if you observe it carefully, we can see in the MNIST there are 10 image per class. For 0, 1, 2 to 9, we have 10 image per class. And for the CIFAR 10, from horse to different animals, we have like 10 image per class. If you look at the horse image or 0 or 1 image, we can see that it is able to preserve the distinctive pattern of the real data using only 10 image per class. So in case of comparison, we try to compare with like no defense case, which is the best case, then regularization, which will be a combination of weight decay and level smoothing. We compared with adversarial regularization that tries to maximize the model's performance, and at the same time it trains an adversarial model which tries to minimize the accuracy of the attack model. And DMP is a knowledge transfer, which is distillation for membership privacy. And also we compared with DMP when that is synthetic data is used. We use also compared with KCD in a separate table. So in most of the approaches, our approach PLDK, whenever used like 500 image per class for CIFAR 10 and 100, CIFAR 10 and MNIST, and 5,000 image for CIFAR 100, we can see that AlexNet can retain better performance than most of the state of the art. And whenever you use a smaller CNN architecture instead of AlexNet, it also was able to preserve better privacy utility trade-off compared to all the state of the art models. And if we pre-train our data with some synthetic data before knowledge transfer, it also ensures better performance than all the approaches. So it shows that we can also use synthetic data in conjunction with the distilled data. As for in experiment for PLDK, we compare with adversarial regularizer, weight decay, label smoothing, and in comparison with knowledge transfer, we compare with DMP KCD. So in the DMP paper, they use wide ResNet 28, so we used ResNet 18 to compare with them, and that shows that it also gains better utility privacy trade-off than previous KCD and MEMGuard approach. MEMGuard adds noise to the output or alters the output, and KCD transfer the data based on some disjoint private data. Transfer the knowledge based on some disjoint private data. So we also empirically compare with differential privacy. So differential privacy is the strongest tool which ensures privacy guarantee. Where we empirically compared with them. So DPSGD has a parameter called epsilon, where epsilon indicates different privacy budgets, and the lower the privacy budget is, the higher the privacy it will ensure. And PATE uses knowledge transfer and it also adds Laplacian noise to the output of the model, so that the data model itself is private. So whenever we use 100 teachers in PATE, so our model, a smaller CNN model, ensures better performance than CFAR 10, 100 NMS, and the performance, the utility increased a lot. In case of privacy, it ensured comparable privacy to DPSGD and PATE. So we also compared with KCD and MEMGuard, as we mentioned. So moving on to why PLDK is better. So PLDK does not need public data or extra private data. So adversary cannot even access the distilled data, whereas previous approaches assumed adversary access to the distilled data. And we use a smaller model which can gain comparable performance to state-of-the-art methods. So in the adversarial regularizations, it has access to private data, and adversarial regularization works as a bottleneck in utility. And regular regularization, if you want to increase privacy, the utility, there will be huge cost on utility. And DMP requires public data or additional data fine-tuning, and KIP or other data distillation approach assume that that the adversary has access to distilled data, which makes the approach weaker in some worst case scenario. And in our approach, we ensured that the adversary cannot access the distilled data, because distilled data is generated during the intermediate phase of the process. And we also restrict the model's access to the private data, so that model cannot leak any private information. So in the ablation study, we tried to identify whether knowledge transfer or data distillation are really important component in our approach. So whenever in knowledge transfer we use only distilled data, it drops utility by 5%. And DT plus KD indicates our regular model, and no data distillation, no knowledge transfer indicates the one of the component is missing during one of the rows. So we also compare the existing data condensation method like DSAA, DM, KIP, which are the state-of-the-art methods, which cannot provide better privacy compared to our approach. And without data distillation, we tried to use synthetic data to transfer the knowledge. And in case of synthetic data, we use transgan, one of the state-of-the-art methods that can ensure better performance. Has a FID score of 9.2, but still it degrades utility by almost 4 to 5%. We use DPGAN, which deteriorates privacy a lot because it adds a noise to the gradient of the model. And we also use public data, which results in comparable performance to DMP. So now data distillation, noise distillation combination ensures best privacy utility trade-off. We also tried to tune the alpha value, which controls the trade-off, and lower alpha reduces privacy, but increases utility. And different model and data size is are also tested to see how which model size will be better. So it shows that heavy model improves utility, but it reduces privacy. So we tried 10, 50, and 200 image per class for CFAR 10, 100, and NMIS, where it shows that 50 image per class can increase better utility privacy trade-off. And in the conclusion of future work, we want to mention that our approach offers a solution to prevent MIA without needing extra public data. reference data tuning or adjustment, and it does not need repetitive access to private data like previous approaches. Our competitive advantage is that the model is as lightweight as a half-inch size, and the inference efficiency is much higher, and is more practical because it does not can be directly deployed in edge devices. And our extensive experimentation has confirmed that PLDK can provide a better trade-off, and it is more suited to practical medical database scenario. And in future work, will try to extend this distillation approach to textual and tabular data in the future, because still now our approach works is mainly suited for like image data, but we'll try to extend our approach for like textual and tabular data. Those are the reference and top references listed, and the detailed references are listed in the paper. And thanks, that's all from me. So please feel free to ask any question. Thank you.